Hello. In the next two videos, we are going to derive the pi molecular orbitals of benzene C₆H₆ using the projection operator method. Our first step is to sketch the carbon ring system and to label the relevant pz orbitals. We imagine that the plane of the benzene ring is the xy plane, and that these labeled p orbitals are perpendicular to that plane, and they're the pz's. We've taken the liberty of labeling them from p1 through to p6. We also recognize that the molecule benzene belongs to the point group D₆H, which has 24 symmetry operations. Our first step is to derive a reducible representation for the pi conjugated system. To find each of the characters for this reducible representation for the pi system, we want to see under each class which of the p orbitals move, which ones don't move, and the character will be the number of orbitals that don't move under the operation. Our first operation is the identity. Since each of the orbitals doesn't move under the identity, our character here is going to be a 6. For the C6 operation, that takes P1 to P2, P2 to P3, P3 to P4, P4 to P5, P5 to P6, and so on. Since each of the p orbitals moves, none of them doesn't move, and our character is therefore going to be a 0. For the C3 operation, which like the C6 and the C2 here, all have the z-axis as the axis of rotation. So for C3, it takes P1 to P3, P2 to P4, P3 to P5, P4 to P6, for example. So since each of the orbitals move, none of them doesn't move, and our character is going to be a 0. For the C2 operation, this is going to take P1 to P4, P2 to P5, P3 to P6. Since each of the orbitals moves, none of them doesn't move, and our character is therefore going to be a 0 here. Next, we have the C2 prime. The C2 prime axis runs through atoms of the ring. That's why it's the prime in this case. So for C2 prime, this takes P1 into minus P1, it takes P4 into minus P4, it takes P6 to minus P2, takes P5 to minus P3, for example. So since two of the orbitals, P1 and P4, are turned into at least some version of P1 and P4 respectively, therefore we can say that we have a character of 2 because two of the orbitals stay in the same position. But we notice that the p orbitals have phase. One half of the orbital is positive phase, one half is negative phase. And if we do this particular C2 operation, when we turn P1 to minus P1, we've changed the phase. And we do the same thing for P4. So to account for the fact that these two orbitals have changed phase, even if they haven't changed their physical location, we have a character of a minus 2. For C2 double prime, this is the axis that runs between two carbon atoms. So for example, if we have this particular C2 double prime, it takes P1 into minus P6, takes P2 into minus P5, takes P3 into minus P4. Since all the orbitals move, in addition to changing phase, our character is going to be a 0. For the inversion operation, I, this takes P1 into minus P4, P2 into minus P5, P3 into minus P6, for example. Since all the orbitals move, our character is going to be a 0, since none of them stays in position. For our improper rotation S3, recall that S3 is a C3 followed by a reflection in the plane of the whiteboard. As soon as we do the C3 operation, we takes P1 to P3, P2 to P4, for example. Even before we do the reflection, we've moved the physical location of the orbital. Since all the orbitals move their physical location, none of them stays put. So therefore our character is going to be a 0. Similarly for our improper rotation S₆. S₆ is simply a C₆ followed by a reflection in the plane of the whiteboard. As soon as we do the C₆ part, that takes P1 to P2, P2 to P3, and so on. Each of the orbitals has moved, so the number of orbitals that hasn't moved is a 0. Now for the horizontal mirror, σH. Remember that our horizontal mirror is the plane of the whiteboard for this particular point group. So that takes P1 into minus P1, P2 into minus P2. This reflection in the plane of the whiteboard takes the positive phase into the negative phase. So we get a change of phase for each of the 6 orbitals, even though they don't change their physical location. Therefore, our character is going to be a minus 6. 6 because each of them stays in the same physical location, and the minus sign accounts for the fact that each of them has changed their phase. ΣD is a mirror plane going between the atoms. So now since it's a mirror going like this along this particular plane, it takes P1 into P6, but it takes the positive phase of P1 into the positive phase of P6, so they don't change phase. But they do all move their physical location. P2 goes to P5, P3 goes to P4, for example. So therefore, the number of orbitals that don't move is equal to 0. Lastly, for our σV, σV is the mirror plane that goes through atoms of the ring. So it takes P1 into P1, P4 into P4, P2 to P6, and P3 to P5. So since P1 and P4 stay in the same position, they don't move, our character for this particular class is going to be a 2. So now we have developed a reducible representation for the pi conjugated system of benzene. But we notice one thing which will help us in our derivations going on is the fact that only 4 of these characters are non-zero. And that will assist us in our work in the next step. Our next step is to reduce this reducible representation into a linear combination of irreducible representations from the point group D₆H. Now we notice that in our diagram here that there are 12 classes. Since there are 12 classes in D₆H, that means there have to be 12 irreducible representations. And we need to derive and see how many of each of those irreducible representations form a linear combination that gives us this reducible representation. So the first irreducible representation in the group is A1G. So our first step is to determine how many operations there are in the class, in the point group. So we know that there are 12 classes, but we need to add up all the coefficients here to see how many total operations there are. And it turns out that there are 24 symmetry operations in D₆H. So our first step in the reduction formula is our 1 over the order of the group, which is 1 over 24. Now we go through and we multiply 3 numbers for each of the classes, one by one, in the point group. Now, since most of these characters end up being 0, we can omit all of these. So we only need to concern ourselves with the classes in the point group where the character of the reducible representation is not equal to 0. So the first such case is for E. So our first number in our reduction formula is the number of operations in the class, and we can imagine that there is a 1 there, even though it's not written, so we have our 1. And then we multiply it by the character in the reducible representation, which is our 6 here, and we put that in purple just to color code it. And the last factor in the first term is the character from the irreducible representation A1G. And recall that all the characters for A1G are 1s because it's the totally symmetric representation. And we can also verify that by consulting the character table for A1G. So this is the set of 3 factors for the E operation. Next, our next non-zero character is for C₂'. So the first factor is the 3, the number of operations in the class, which is a 3. Then we multiply by the character in the reducible representation, which is -2. and then we multiply it by the character in the irreducible representation, A1G, and that is a 1. So this is for the C₂ class. Our next non-zero character is for the sigma-H operation. So again, whenever there isn't a coefficient, we can imagine that the coefficient is a 1. So there's one operation in the class. We multiply it by the character of the reducible representation, which is -6, and we're color coding that all through the way. And then the character for the irreducible representation, A1G, is a 1, which we get from consultation of the character table for D₆H. And our last class is sigma V, and we have 3 operations in the class. The character from the reducible representation is a 2, which we put in purple. And then the character from the irreducible representation, A1G, is a 1. So we notice we have 6, -6, -6 plus 6. So it turns out that there are no A1Gs in the reducible representation gamma sub pi. Now this may be surprised by comparison with sigma orbitals, where when we derive the sigma orbitals for a particular molecule, we will always have one combination that corresponds to the totally symmetric representation. This will not be true when we're deriving the pi molecular orbitals. To speed up the derivation, we're only going to now derive the irreducible representations that are actually included in the pi conjugated system. And the first such of these irreducible representations is B2G. So the derivation, we have our 1 over the order of the group, which is 24. We have our number of operations in the class, which is going to be 1 for E. Our character from the reducible representation is again a 6. And our character from the character table for the irreducible representation B2G is a 1. So one thing which you'll notice is that as we do these derivations, the first 2 factors in each term will always be identical. The only number that changes is the number in black, the third factor, because that depends upon the irreducible representation, and that will change. So our second term, the number of operations in C₂ is 3. The character from the reducible representation is -2. And then the character from the irreducible representation, B2G, is a -1. Now for sigma H, the number of operations in the class is equal to 1. The character from the reducible representation is a -6. And the character from the character table for B2G is a -1. And then for our last term, corresponds to sigma V, our vertical mirror, 3 operations in the class. The character from the reducible representation is a 2. And the character from the character table for B2G is a 1. So we have 6 plus 6 plus 6 plus 6, which is 24. That tells us that we have 1 B2G included in our gamma sub pi. The next irreducible representation that we need to include is E1G. So we have 1 over the order of the group, which is 24. The number of operations in the class for the identity is equal to 1. The character from the reducible representation is a 6. And then the character from the character table for the irreducible representation E1G is a 2. And that makes sense because this is a doubly degenerate representation. Then for C₂, the number of operations in the class is equal to 3. The character from the reducible representation is -2. And then the character from the character table for the irreducible representation E1G is a 0. Now we have sigma H, our horizontal mirror. The number of operations in the class is 1. The character from the reducible representation is a -6. And then the character from the character table for E1G is a -2. And then our last class is the 3 sigma V's. So we have 3 operations in the class. The character from the reducible representation is a 2. And then the character from the character table for E1G is a 0. So we see we have 12 plus 0 plus 12 plus 0 is 24. 1 over 24 divided by 24 is equal to 1. So far we have a 1 B2G and 1 E1G included in our reducible representation. Our next irreducible representation, irrep, is A2U. The number of A2U's we have in here. So again, we have 1 over 24. And then recall that we have one operation in the E class. Our character from the reducible representation is a 6. And then our character from the character table for A2U is a 1, which makes sense because this is a non-degenerate representation. If the Mulliken symbol is an A or a B, that tells us it's non-degenerate. Our next class is C₂'. There are 3 operations in the class. Our character from the reducible representation is a -2. And then our character from the character table for A2U is a -1. Our next class is sigma H, and there's 1 operation in the class. The character from the reducible representation is a -6. And then the character from the character table is a -1. Sigma V, there are 3 operations in the class. So we do that in red. The character from the reducible representation is a 2, so we do that in 2. In purple. And then the character from the character table for A2U is equal to a +1. So now we have 6 plus 6 plus -6 plus 6, which gives us a total of 24, which is equal to 1. Our final irrep to look at is E2U. To see how many of those are included in our reducible representation, we have 1 over 24. And then again, continuing with the E operation, we have 1 operation in the class. The character from the reducible representation is a 6. And then the character from the irreducible representation for E2U is a +2. For C₂', there are 3 operations in the class. The character from the reducible representation is a -2. And the character from the character table for E2U is a 0. For sigma H, there's 1 operation in the class. The character from the reducible representation is a -6. And then the character from the character table for E2U is a -2. For sigma V, there are 3 operations in the class. The character from the reducible representation is a +2. And then the character from the character table for E2U is a 0. So we have 12 plus 0 plus 12 plus 0. So a 1/24 of 24, which is equal to 1. So what we've shown is that we can write the reducible representation gamma sub pi, this tells us about the pi conjugated system, as a linear combination of A2U plus E2U plus B2G plus E1G. And recall, since we started with 6 molecular orbitals, we expect that we're going to derive 6 combinations for the molecular orbitals. We notice that here we have 1. E2U counts as 2. Since it's doubly degenerate. B2G counts as 1 because it's non-degenerate. And then E1G counts as 2. So we have 1 plus 2 plus 1 plus 2, which is equal to 6. So that checks that we've derived the correct number of pi molecular orbitals for benzene. I thank you for your attention. Please tune in to part 2 of this video to see what these actual pi molecular orbitals actually look like. I thank you for your attention. Have a good one.